Okay, so this is our lecture 10, number 2 on acid and base calculations. And before we talk about calculations with acids and bases that are kind of unique and new to this chapter, let's just do a little bit of review of some stuff that we have done in the past, okay, because it's all built on itself. And so we remember from chapter 6, we made this little roadmap so we would know where to go when relating between, say, grams of one substance or moles of one substance to moles or grams of a different substance. Obviously, within the same thing, if I'm going from grams to moles, I use the molar mass, but if I'm crossing inside of a reaction from one thing, A or B, to the other thing, A or B, then we have to use coefficients of these balanced equations. And that is part of what is going on here. So in other words, if I've got this reaction that says I've got carbonate reacts with HCl to make HCl3 minus and chloride, and this is balanced, there's one of each of these here. Then if I know how many grams of HCl that I've got to start, then I can calculate how many of moles of HCl that is, and I could go on to calculate how many moles of carbonate that would react with and how many grams of carbonate that would be. Does that sound a little bit familiar? Do you guys remember doing that? I know that was exam 3. It was like a month ago, chapter 6. But we built on a little bit already. Okay, good. And then last chapter, chapter 9, we added this extra little fun thing and said, hey, if I know moles, I can discover my concentration in molarity if I've got volume, right? If I'm a solution, I know moles, and volume, I can determine molarity. And I could do that because molarity has what units? Yes, moles per liter. Excellent. So if I have moles and I know volume, I can put that in liters. I can determine molarity, which is moles per liter. Or if I'm given molarity, I can use volume to go back and find moles. And now that I'm plugged into my roadmap, I can find whatever the heck else it is that I'm looking for. That's what section 3 is about. So section 3 is not anything new. This is just reminding us of what we already know how to do from what we learned in solution concentration units on chapter 9. What just happened there? My thing's going crazy. Okay. Sorry, I'm gonna have to fill that in again. So this is chapter 9, all over again, nothing new or different. I'm just applying it then specifically to these reactions which I have defined as acids and base reactions. That's all. So for instance, with the first one, the first question says how many moles of HCl will react with 32 milliliters of 0.10 molar carbonate. If we look at our roadmap, we're going to say, all right, moles of HCl, that's what they want. They want moles of something, all right? We could call it moles of A or moles of B. Let's call it moles of A. It doesn't matter which one we call it because they wanted moles. I selected moles. And now I have defined A as HCl. Okay, and what did they give me? They gave me the volume of a carbonate solution. Is this carbonate, is that the same thing as HCl or is that something different? It's different. So if HCl is defined as A, then I better define my carbonate as B. Okay, so they gave me the molarity of B and the volume of B. So they gave me molarity of B and the volume of B. Okay, these two things. All right, now being able to see it on the roadmap, can you guys tell me how I might get from here, this information given, to here, this information requested? Yeah, this piece I'm going to use the mole to mole ratio. How am I going to get to here? How do I get from here to here? Using your molarity and your volume. Okay, and all of this is dimensional analysis. So let's start with what we're given here. We're given, we can start with the volume or we can start with the molarity. It doesn't matter. Joyce says use the molarity. Okay, use that capital M. And remind me, because the capital M is useless, what do I need to use instead of capital M? Perfect, moles per liter. Because I can't do dimensional analysis with capital M, but I can do dimensional analysis with moles and liters. Okay, and this is again moles of bicarbonate solution per liters of that. It's not liters of carbonate specifically, but it's liters of the carbonate solution. And I want to make sure that I preserve that. Okay, I have moles per liter, and I want to get to, my first step is to get to just moles. So how do I get rid of my liters? Perfect. They gave me the volume of the carbonate solution. Now be very careful because this is milliliters and I want liters. That's going to be 0.032 liters. Okay. So very careful with that. If you wanted, you could put the 1 liter is 1,000 milliliters and then put your 32 milliliters there, and that would get it. But careful, careful, careful when you're doing that conversion that you go as far as you need to. So 0.032 liters of my carbonate solution, 0.032 minus. And again, this is not a conversion factor, it's just information that I use. So I don't need something on top and bottom. I just put that where I want it to be so that I can cancel out the volume. Excellent. Okay, so now I have moles of carbonate. Sweet, I got to this block here. And now the roadmap says I can get from here to there using the coefficients of the balanced equation. Let's look at this balanced equation again. It looks like 1 carbonate reacts with 1 HCl to make 1 hydrogen carbonate and 1 chloride. So what do I put here in this last slot? Ratio of coefficients. Yes, thank you, Joyce. That's exactly what I wanted to see. It is 1-to-1 and it is 1 mole to 1 mole, but if I want to be very careful and specific about what I'm doing, it's 1 mole of HCl on top and then 1 mole of carbonate on the bottom. Why is that important? Why should I say 1 and moles and HCl carbonate, that kind of thing? Why should I include all that? Yeah, Joyce, correctly recognizing here that I have moles of carbonate and that's what I need to cancel. So I have to put this on the bottom in order to cancel that. Okay. And if I do that, I'll be left with moles of HCl, which is exactly what I asked for. Yay! And that's how I know that that's what I want on top, because that's what I need in my answer. All right. Is it always going to be a 1-to-1 mole ratio? Of course not. Am I going to give you a 1-to-1 mole ratio on the test? Of course not, because then that would mean that I'm not testing on whether you can apply the step properly. No, I'm going to give you a harder one with maybe a 2-to-1 mole ratio or something, all right? So you're going to have to Make sure that you have everything in the right spot. This one you could have gotten lucky if you didn't put the right thing in the right spot. But that's it. Now I'm at moles of A and I can stop and I'm done. And so I just plug this in 0.1 multiplied by 0.032. That should give me 0.0032 moles of HCl. Okay. Again, this is literally stuff from last exam that we just took. This first step was solution concentration units from chapter 9. This step was multiple ratios from chapter 6 that we put together. And I think there was at least one question like this on the test. So this was kind of the hardest thing that we had to do on our last exam. But this is the starting point then for the next set of math that we're going to do for this chapter. So again, chapter 10 really brings everything that we've done before and puts it all together and builds on it in really fun ways. So that's what we're looking for. So section 3 is all review, and it's plugging in things about solution concentration units, or molarity, or asking for concentration, with your multiple ratios on these equations. So using these equations right here. So equation 2, here now I'm asking for grams. Let's do this one. Nothing wrong with that. Actually, let's do number 3, because it's asking for something slightly different. So number 3 says they give me a volume of NH4. They ask for the concentration of, hopefully if you read this carefully, you see they're looking for the concentration of NH4 plus. And then they give us the moles of cyanide. Okay, so moles of cyanide, where would that be on my roadmap? Moles of cyanide. Trying to get you guys used to using the roadmap, because I do give you the roadmap on the test, right? Perfect. It's in the middle because it's moles. So you're like, all right, where's moles? Here's moles. And I could define cyanide as being either A or B. Does it matter to you guys? It doesn't really matter, but does it matter to you? Which one would you like it to be? Apparently it doesn't matter to anybody. I'm going to make it B. No, it matters to Robin. I'm going to make it A. Moles of A, this is what they gave you. So A defined as cyanide for the purposes of this problem. Okay. They gave you moles of cyanide, which we're defining as A. So they gave you moles of A. They're asking for concentration of ammonium. What are the units of concentration? Where would that be? Molarity, okay. And is ammonium, is that going to be A or B? It's going to be B, because I already defined A as being cyanide, and ammonium is definitely different than cyanide. So now we have to say, okay, so B then is my ammonium. And they want concentration, which is molarity. So they want us to get here. And they did give us this piece of information as well. Okay, so they gave us moles of A, they gave us volume of B, and they want us to go from moles of A to molarity of B. All right, can we do that using the roadmap here? You guys help me out. What's my first step going to be? My first step would be to balance that equation, right? But it's balanced, so that's good. Okay. I was given moles of A, I was given volume of B. This is my final destination here. So starting from my furthest point, first thing I have to do is what? Hang on a second, Robin. We're going to need to do that, but not quite yet. We will use the volume, but that's the last step to get us here, right? If we start on the outside, start from my furthest position, I need this to find that. And then once I have this, I can use this and this to find that. Okay, but yeah, we have to start with 0.38 moles of cyanide. Okay, so 0.38 moles of cyanide. And do we need volume of cyanide? This would be volume of cyanide, right? A is cyanide. If I use volume of cyanide, is that going to get me where I need to go? No, that would be going this direction, which is a perfectly valid direction to travel if I wanted you to go that direction, but I don't want you to go that direction. I want you to go this direction. This is where our destination is. So the first thing we need to do then is use this to get from point A to point B. So what are the coefficients of that balanced equation? Oh, Jackie got it. Yes, you had it right there. 0.38 moles of cyanide times, there's our, sorry, Jackie, I didn't see that in there. 1 mole of NH4 plus over 1 mole of cyanide. Excellent. We take that step, multimole ratio, that gets us here. We're at moles of NH4 plus, and NH4 plus was B, so that means that we're here. So now the step is to go from moles of B to molarity of B, and I've got volume. So what are the units of molarity again? Exactly, moles per liter. I've got moles of NH4 plus. So what do I need to do now to get moles per liter? Liters on the bottom, that'll give me moles per liter. Okay, so what, I mean, I can't just put liters on the bottom. I have to have a number that I'm using or a conversion factor or something. Where is that? What do I put on the bottom? Perfect. Here's the liters of NH4 that I can put on the bottom. Liters of my ammonium solution. Okay, that's good because we need, if we're talking about concentration, we better be talking about a solution that has the moles of that thing and the liters of that thing too. Okay, perfect. That'll give us moles per liter, and that's the units of concentration, and we're done. So then we're going to have 0.38 divided by 1.5, and that will give me a 0.253 molar solution. That's my answer. Now again, this first step was just multimole ratio stuff that we learned in chapter 6. The second step, taking the moles divided by liters, is just concentration unit stuff that we learned in chapter 9. And we can just use dimensional analysis to set it up and go. And if we want to make sure that we're going the right direction, because there's so many directions we could go, we might want to use the roadmap. Okay. Now, these two are essentially the same as these two. Equation 2 is just like equation 1. You just have this extra step of calculating grams once you find moles, right? Equation 4 is just like equation 3, except with this extra step of, instead of starting with moles, we start with milligrams, right? So it's just, I'm adding in this molar mass conversion, but they're identical. And I need you guys to practice these. It's going to be more effective for you guys to sit down and work it out so that you can see what you're doing, so that I can make sure that you can do it again for the test. So I'm going to leave these for you. But again, you guys should be able to do these. This is exactly the type of question that we saw on the test that we just had. Okay. Any questions on this before we move on? Okay. All right, next, acid-base calculations. This should be a familiar roadmap from chapter 6. Here is a set of equations that I give you on the exam that are pertinent specifically to chapter 10 material. And that is, when it comes to acids and bases, and particularly when it comes to acids which are donating your H plus and bases which have an OH minus to accept it. What we find is that there's a huge range of concentrations that we can see that we would call acids and bases. Part of this comes from the fact that water naturally dissociates to form H plus ions and hydroxide ions. Okay. Not a lot, just a little teeny bit, but a measurable amount such that the equilibrium equation for this reaction, which is the H times the OH minus, is equal to 1 times 10 to the negative 14th. In other words, dissociates just a tiny, tiny bit, but a measurable amount. And this is an equilibrium value, okay? Which means that Le Chatelier's principle tells me that if I add a bunch of H plus to solution, then it's going to react with the OH that's available to make water, but my K value won't ever change, okay? Because it's reestablishing that equilibrium, reestablishing the K value. So my H concentration times my OH concentration will always be 1 times 10 to the negative 14th. What this means is that your concentration of H or OH can vary from between about 0.1 molar all the way to 0.1, 2, 3, 4, 5. Oops. There we go. To that concentration. Very wide range of concentrations for acids and bases in solution. It's huge. Nobody wants to deal with numbers like this. So in order to avoid dealing with numbers across such a wide range, we take the log of those numbers, log base 10. And in fact, because these numbers are smaller than 0, we take the negative log to make it a positive number. And so we're going to take the negative log of the H plus concentration to find what we call the pH, and the negative log of the OH minus concentration to find what we call the pOH. And on a normal range for acids and bases, that normal range runs from 0 up to 14, because the concentration ranges from 1 to 1 times 10 to the negative 14th. That's where this comes from. And each point on that scale represents a 10 times increase in acidity or basicity, right? So your pH scale goes from 0 to 14, and the middle point, 7, is what we would call neutral. And if I'm between 0 and 7, then I am acidic. And if I'm between 7 and 14, then I am basic. Okay, you guys ever seen the pH scale before? Usually I've had people at least kind of heard of it if you haven't worked with it, kind of thing. But 7 then is neutral, 0 to 7 is acidic, 7 to 14 is basic, and the pH then is just the power, the P stands for power, the power of the hydrogen ion. So if I'm from 0 to 7, I have a larger hydrogen ion concentration than hydroxide ion concentration. Since I've got more hydrogen than hydroxide, I'm acidic. Between 7 and 14 then, I have a lower hydrogen than hydroxide because I have more hydroxide than hydrogen. That makes me basic. Anyways, all of these equations here, come from this idea. First of all, that the K value, that the equilibrium ratio between the two of these is always 1 times 10 to the negative 14th. And the power of each of them is the minus log of that thing. Okay. We're going to just deal with kind of 1 or 2 of these equations at a time. But again, you will not have to memorize these. They will be on your equation sheet for the exam. These brackets mean concentration, which means you can go from moles of B to concentration of B if you're given the volume. And if you've got the concentration, then you could go to pH or POH by plugging it into this equation. So we're just adding to our roadmap, just extending our roadmap by an extra step. Concentration of A, I've got the concentration of A, I can go to pH or POH, okay? And in fact, at this point, it might be convenient to say, hey, A is my acid and B is my base, right? And that would be a concentration of your base that could take you to your power of the hydroxide. Concentration of your acid, that might take you to your power of the hydrogen, okay? All right, so the takeaway here is if you can find your hydrogen concentration, then you can predict your pH. Or if you can find a hydroxide ion concentration, you can predict a POH, all right? And these two things are related. My pH plus the POH will always be equal to 14. So if I can find the pH, then I can use that, plug it into this equation, and I can find the POH. That's how it works. Let's give just a couple examples and then we'll do some practice problems. So number 1, if I wanted to know the pH of a solution, and I said this solution contains 0.0150 molar hydrogen ions, well, I said, what's the pH? You would say, oh, well, you gave me concentration to start. I can just go straight to pH by using the pH as the minus log of the H plus. And we're going to plug this into our calculators. Now, you need to practice this in your calculator because every calculator is different. It's easy enough to say, okay, here's the equation that I want to use, minus log of the H plus, which in this case is 0.0150. For some of you, your calculator will want you to hit the minus sign and then the log sign and then enter 0.0150. For some of you, your calculator will want you to enter 0.0150 and then hit the log button and then hit the negative button. Each calculator is a little bit different, so you're going to have to determine what your calculator wants. I believe this calculator wants me to put 0.0150 and then hit the log button and then make it negative, and that gives me a pH of 1.82. Did you guys see what I did there? Every calculator is going to be different, so you have to practice this on your calculator before we get to the test. Have to. Did you guys get the same answer as me? No, it should not be a negative answer because the log of 0.0150 is negative, and then we take the negative of that, right? So when I put 0.015 and I took the log, that gave me a negative answer. And then I said, okay, but I want the negative log. So that brings it into the positive range. Okay. Now, just to make it a little bit more confusing, I might not give you the concentration of the H plus ion. I might give you the concentration of the whole acid. Like I might say we've got, let's say I've got 0.0125 molar HCl solution. And I said, what's the pH of that? All right, we want just the H plus, not the HCl. But, and this is important, any of our strong acids will dissociate completely. This is one reason that I have you guys memorize this list of strong acids. So here's HCl, dissociates completely. So we know that HCl is going to form H plus and Cl minus. 1 mole of HCl gives me 1 mole of H plus and 1 mole of Cl minus. So if I have 0.0125 moles of HCl in a liter of HCl, and I've got 1 mole of HCl produces 1 mole of H plus, I hope you guys could see, and maybe even without doing that math, that essentially I've got 0.0125 molar hydrogen ion solution. And that's what I can plug into my pH equation to say my pH is the minus log of my 0.0125, because that's my H plus. All right, so if I give you the whole acid rather than just the hydrogen ion, then pulling out how many hydrogen ions are formed by that acid and then plugging it in is the next step. Okay. Anybody confused by what I did there? Any questions in particular? I haven't done the math yet, but I can, and let's make sure you guys get my same answer. 0.0125 log negative log gives me a pH of 1.90. Any questions on that? Or no questions on that? I'd feel better if at least 2 of you said no questions. Or if at least 2 of you said, I don't know what question to ask, but I'm confused. Okay, just need to figure out the calculator. Yeah, every calculator is different. And if you bring it to class on Wednesday, that's one thing that we can do to make sure. Typically, the graphing style calculators want you to enter the equation as is. So they want you to enter the negative sign and then hit the log button, and then for the parentheses, fill in the parentheses and then hit enter. Whereas the smaller, just plain scientific calculators want you to go backwards and put in the number and then hit the log and then the negative sign. So we can do that in class on Wednesday. Okay, so that's the pH. Help me out here. Could we find the pOH of this particular solution? Or the pOH of this particular solution? How would we do that? Yeah, that's the easy part, right? The pH plus the pOH equals 14. So if I have the pH, I just subtract the pH from 14 and I'll get the pOH. Excellent. So pOH is 14 minus 1.82, which in this case, because I'm lazy, is going to be 12.18. In this case, it's going to be 14 minus 1.90. So that's going to be 12.1. Excellent. Okay. Now, that's excellent, excellent, excellent. What if I gave you a base? What if I said we've got, say, sodium hydroxide solution at 0.0105 molar. And now I want to know what the pH is. How would I do that? Because this doesn't have a hydrogen ion. It's a base. I hope you guys can recognize it's a base. That's the first thing that we did today, was recognizing acids and bases. Yes, yes, that's exactly right. Because we have hydroxide, we have to find the power of the hydroxide. Once we find the power of the hydroxide, it's easy to plug that in and find the pH. We don't have a hydrogen ion, so we can't measure the hydrogen ion directly. We can only measure it indirectly by first measuring the power of the hydroxide. Yes, 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 perfect. Okay, so we know that sodium hydroxide is going to split up to sodium and hydroxide, that 1 mole of sodium hydroxide splits up to 1 mole of sodium and 1 mole of hydroxide. So a 0.0105 molar sodium hydroxide solution, that's the same thing as a 0.0105 molar hydroxide solution. Okay, how do we go from there to determining the pOH? What's the formula we're going to use? Yes, 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 yes. The pOH is the minus log of the OH minus concentration, which in this case is 0.0105. Therefore, the pOH is, anybody have this plugged in before I get to it? Excellent. This gives me a pOH of 1.98. Yes. All right, good. Now we can't stop there. We have to remember they asked us for the pH. So in that case, what is the pH? Yes, 12.02. And again, we got that by saying 14 minus 1.98. Perfect. Perfect. Okay. The key for these ones is to recognize using which equation to use. My pH is the minus log of the H plus concentration. My pOH is the minus log of the OH minus concentration. And there's a direct relationship between the two of them that actually stems directly from this equilibrium equation. Okay. These equations will be given to you, so you don't have to remember them. The key is to remember which one to use when. Again, if I give you an acid, you're going to plug it into this one to find the pH. If I give you a base, you're going to plug it into this one to find the pOH and use that then to find the pH. Now, there's technically two scales, right? There's the pH scale, and then there's the pOH scale, which is related. But chemists decided, look, let's just deal with one scale so we don't have to deal with both scales. So they settled on the pH scale. So once you find the pOH, you just convert it to the pH. You just use this thing right here. Okay. Now again, this adds another section to our awesome roadmap. If we have the concentration, we can plug that in to find our pH and or POH. So in our in-class activity sheet, actually, we can do this one right here. It's if we know the concentration and the volume of my acid, I can use that to calculate moles of acid, use that to calculate moles of base. I'm given the volume of base, so I can use that to calculate the concentration of base. And then I can use that to find the POH and then for the pH. So this is exactly that type of equation, exactly like the one that we just did here, but then adding an extra step of calculating pH or POH when we're done. Okay. All right. So we can plug that in. Section 4 here. Sorry, let's back it up and make it simpler. Section 4 here has you calculate pH. So if I give you your concentration of your acid or your concentration of the base, you could calculate the pH directly. If I give you moles and liters, you could use that to determine concentration and then use that to calculate pH and POH. And if I give you grams or milliliters, you can convert that to moles and liters. You can convert that to concentration and use that to calculate pH. Okay. Before we do these with you, I want to just talk about the inverse first, because you're going to need to be able to go backwards as well for some of these problems. So the inverse calculation is to say, if I know the pH, how do I find the H plus? How do I go this direction? And this is properties of logs, that the inverse is the 10 raised to. Again, you're going to get all of these equations on the exam. You don't have to memorize anything. You just have to know which one to use when. So this is kind of cluttery. Let me clean this up a little bit. Oops. There we go. If I ask for pH, you need to plug in the H plus, and that will give you pH. If I give you pH, then you can plug in the pH here, and that will give you your H plus ion concentration. So to go this direction, you use this formula. And if I want to go that direction, we're going to use this formula. It's just the inverse of, one is the inverse of the other. Like multiplication is the inverse of division. So if you want to go the opposite direction, instead of the log, you have to do 10 raised to the negative. And again, everybody's calculator is going to be slightly different, okay? So, for instance, if I asked, what is the hydrogen ion concentration of a solution with a pH of 3.2? So pH is 3.2. And I said, what's my hydrogen ion concentration? We're going to say, all right, my H plus is 10 raised to the negative pH. Everybody's calculator is different. I think this one's going to want me to put in the pH and then hit the negative sign and then hit the 10 raised to the X button. Some of yours are going to want you to hit the 10 raised to the X button and then put in the negative pH. Again, you're not looking for the exponent button. You have to use a 10 to the X or an X to the Y button. Either one of these. If you use X to the Y, you have to define X as 10 and Y as your negative pH. I think this one will work here. So if I put 3.2, make it a negative, and then I'm going to take 10 raised to that. That gives me an H plus concentration of 6.31 times 10 to the negative fourth. Everybody take a minute with your calculators and see if you can't get it to give you that same answer. If you use the X to the Y, you're going to define X as 10. hit x to the y, and then say 3.2, define that as your y, and then hit enter. You should get the same answer. I want at least 2 of you guys to tell me that you can get that answer. Can and or did get that answer. Yay! That's good. Hooray! Awesome. Okay. Excellent. Okay. So again, this is the inverse calculation. And so both of these calculations, or I should say all 4 of these calculations here, are what we're using for this conversion here. So if I number this as like number 1, 2, 3, and 4, number 1 will define pH. Number 2 will get me back to concentration. Number 1 will find me pOH. Number 3 will find me pOH. Number 4 will get me back to the OH minus concentration. And from there on out, this is the only new thing in this section. Everything else is, this is holdover from chapter 9, going back and forth from concentration to moles. This is holdover from chapter 6, looking at a reaction and the mole to mole ratios. And that, putting these extra steps in with these steps that we're already familiar with, should allow us to do almost everything that's left on our in-class activity sheets here. So from our 10-1 in-class activity sheet here, this is just practice calculating the pH. But then if I give you an equation, you start with pH of an acid solution. You can use that to find the concentration of your HCl. From there, you should be able to find the moles of HCl. From there, you should be able to find moles of carbonate. Okay, just using your roadmap. Kind of same thing for each of these from 10-1. From 10-2, this is practice going backwards. So my H plus is 10 to the negative 4.5, kind of a thing. Each of these is kind of plug and chug. And then, again, calculate the pH if I know this information, or if I know what pH I start with, and kind of go backwards. And you guys should take a stab at all of these, or at least at 1 or 2 from each section, and then we'll review them in class on Wednesday. The second page of the 10-2 in class activity sheet, that's the only new stuff that we haven't gotten to today, and we might not do it till next Wednesday, because I think we've got enough, or sorry, next Monday, because I think we've got enough to cover in class on Wednesday. So put a good stab into this stuff, guys. It's not really hard, it's just extra steps. It makes it an extra piece of complication, but not difficult, if that makes sense. Anyways,